We have another video that's going to do a little bit more challenging kind of derivatives that are going to involve the chain rule. And I know that it's a chain rule because I have a function within a function, right? And so when I do my chain rule, I'm going to be doing the derivative of the inside times the derivative of the outside. So let's go ahead and do that. So if I start doing the derivative of this with respect to x, my power is going to come in front, and then my inside's not going to change. I'm going to drop my power down. So that's the derivative of the outside. Didn't change the inside at all. Right? So it's as if I have that. And then times the derivative of the inside. So derivative of tangent is, the way I help remember that is, then I'm going to drop the p. So that represents secant, secant, and tangent. So the derivative of tangent is secant squared. So derivative of tangent is secant squared. And then derivative of 10 is just going to go away. So if I clean this up just a little bit, I'm going to have 21 times secant squared x times tangent x plus 10 to the 20th power. All right, there's my first derivative. Second one, also a little bit more challenging, that we have a trig value that's raised, that is multiplied by e to, well, actually it's sine, and then we have instead of just sine of x, we have a value inside of it that's an exponential that has a cosine. So we're going to do the derivative of this one. We have, let's write it out maybe like this time. So we have the derivative of sine e to the cosine x. All right. So we have a chain rule because we have a function that's going to be within this function. So if we do our derivative, we're going to do the derivative of the outside, which is sine. Derivative of sine is cosine. And then nothing changes on the inside. But then we're going to do the derivative of the inside. The derivative of the inside is an exponential. That is, the derivative of an exponential is itself times the derivative of its exponent. The derivative of cosine, derivative of any co is a negative, so it's a negative sine x. So if I clean it up a little bit, how much I can do, maybe kind of clumping these two in the front. I don't know. I have a negative sine x times e to the cosine x times this original here, the original cosine e to the cosine x. All right. And then we got one more. So this one's got a little bit more going on. If our original on this one is y equals x squared, and then as I'm rewriting this, I might as well take this and put it as a 1/2 power, because I'm going to need to do the derivative with a 1/2 power, not as a radical. Now I do the derivative. So I have a product rule going on between them. And when I do the derivative of this one, I have a chain rule that's being applied on this one. So I got a couple little things that are happening. So product rule is the derivative of the first times the second, x squared plus 1 to the 1/2, plus the first times the derivative of the second. So the derivative of the second is, I'm going to bring the power down 1/2, and then x squared plus 1 to the negative 1/2. Right, and then times, so that's the derivative of the outside times the derivative of the inside. Looks like that. All right, so that's the calc. The rest of this is going to be the algebra part. And the algebra part is probably going to be more challenging than the calc part. So let's start manipulating and cleaning up and all those things. So first thing is, I'm going to pull my fractional exponents back as radicals. So then that would mean this one is going to look like this, 2x times the square root of x squared plus 1, plus, I could put these two together, and that's going to be a 2x cubed. And then actually that 1/2 can cancel that 2. So that'll make that a 1. So it'll actually just be an x cubed. And then here I have a negative 1/2 power. which means negative exponent is going to come down and the 1/2 power is going to be a square root. And then x squared times x is going to be x cubed. So I'm looking at that. And then a lot of times they want you to combine all this and put it back to put it together. So, which means we need a common denominator. So extra work. So I'm going to need to multiply this one by a square root of x squared plus 1. So I'm going to multiply 2x and then this piece right here. I'm going to multiply it by another x squared plus 1 just because I want a common denominator. And then this I'm not doing anything with because it has a denominator of x squared plus 1 already. So when I multiply that, that's perfect. That's going to make our denominator square root of x squared plus 1. But then on the top, I'm going to be able to, this square root times this square root, they match. And so the square roots are going to cancel. And you're left with the 2x times x squared plus 1. And then plus this x cubed over square root x squared plus 1. All right. So that was just so we can get a common denominator. And so now we're going to go ahead and distribute. So I'm going to get a 2x cubed plus 2x. And since the denominators match, I might as well push this all together into one fraction with that common denominator. So then I can add the other numerator to it. It's a cube. And then I can combine my like terms, and I should be good. So I have this, the x cubes that can go together. And so that's going to make a 3x cubed plus a 2x. That's the top over this square root of x squared plus 1. And that is our final answer on that. So a lot of times when you're doing these, it's not the calc that's the problem. It's all this algebra that it takes to finish it or complete it or simplify it or whatever the directions are asking for. So, so that was a couple examples involving a little bit more challenging chain rule types of problems.